All right, so something really interesting happens when you combine Bohr's model of the hydrogen atom and another idea that we talked about in a previous video, which was wave-particle duality. So if you recall, the idea was due to de Broglie, and he said, okay, so if we can describe light as a wave and a particle, wouldn't it be possible to also describe the particles of matter as waves and assign them a wavelength? And so de Broglie said essentially, okay, so if the possible orbits of the electrons of the electron in a hydrogen atom were given by integral number of wavelengths of that electron, and then you have something that looks a bit like a standing wave. And so you have some examples here given from different orbits, seeing what it would look like, and essentially fitting some numbers of wavelengths for the electrons. So let's take a closer look and see how that fits within Bohr's model of the hydrogen atom. All right, so if we take a look at the momentum of our electron, we know that by definition, momentum would be mass times velocity, so mv, if we look at the magnitude. And it's also given by h over lambda if we're going to assign a wavelength to our electron. So now the idea is, okay, so what if then we say that on our orbit, we're going to fit a number of wavelengths, meaning that, all right, so if I look at the circumference here of my orbit, so for a given orbit, we know that we are going to have a radius, all right, and you can see that you can label it with the number n that you want. So that means that, so I'm going to do a terrible job. So if we have our electron over here, so we have our radius r, and the circumference is going to be 2 pi r. And we're saying, essentially the idea is that we're going to fit some n number of wavelength on our orbit. Okay, so if we do that, then you can see that we can simplify. We get a momentum, which is nh over 2 pi r. Okay, where n is 1, 2, 3, it gives you the orbit that you're looking at. Now, if we go back and look at the angular momentum, by definition, the angular momentum is mrv, so rmv either way. And you can see that we basically just multiply by r, which would eliminate the r here, and we're left with nh over 2 pi, where again n is 1, 2, 3. And that right here, you may recall, was actually exactly what was predicted in the Bohr's model. So that was our second assumption right there, so that only certain orbits were allowed, and they corresponded to angular momenta that were given by this formula, which is exactly the one that we derive once we add de Broglie's wavelengths to our electron, which is really interesting. So it all fits. So even though the assumption may have seemed arbitrary, you can see that it actually fits very nicely. So up next, we're going to look at quantum numbers, and we're going to see how we can give a quantum mechanical description of the hydrogen atom. All right.